What if I told you that the Apollo astronauts were perhaps the most successful geologists of all time? There's no question that the Apollo missions were a stunning technical achievement. At its height, over 400,000 employees and contractors across 2,000 organizations and private companies worked together to send 7 missions to the lunar surface. 6 of those missions were a success, with a dozen men touching foot on the moon. All told, those 12 people spent 12 and a half days on the lunar surface, with just 3.4 days spent performing extravehicular activities. And in those few days, the Apollo astronauts managed to traverse a total of over 95 kilometers from their landing sites, collected and returned 382 kilograms of rock and soil samples from over 2,000 sampling locations, drill 3 sample cores to depths of over 2 meters, drill another 5 cores for heat flow experiments, take over 6,000 images from the surface, and placed, installed, and activated over 1 ton's worth of scientific gear, some of which is still in operation today. All those activities have resulted in over 2,500 academic publications and counting. Research groups around the world continue to investigate the lunar samples. Roughly 100 people every year visit the Lunar Sample Laboratory facility at Johnson Space Center for research or education. And every year that facility loans out about 400 samples. All of that work, all of that investigation, all of that collecting, all that science is still useful today in less than 3.5 days work. Sometimes it takes me 3 days just to unpack from my vacation. And those dozen astronauts were able to completely revolutionize our understanding of the moon. So what did we learn from the Apollo missions? Besides the cultural and technological impact, what were the scientific implications? What do we know now about the moon today that we didn't know before? And what would we still not know if it weren't for those missions? I'm Paul Sutter, a cosmologist, author, and host, and this is Near Futures. Neil Armstrong almost made a fatal mistake. He had found an interesting rock sticking out of a formation. Curious to see what the rock was made of, he needed to examine its interior more closely. So he reached for his hammer and took a swing. But the rock was far more brittle than he anticipated. And instead of cleaving in two, it shattered. One of those shards flew away with so much force that it left behind a bloody gash on his forearm. Thankfully, Neil's miscalculation didn't take place on the moon, but on a training exercise in Big Bend, Texas. He was learning how to be a geologist, not a fighter pilot or an astronaut, and it's a good thing he had expert guides with him so that he wouldn't make such a rookie mistake during an actual mission. Early on, NASA leaders like James Webb, the administrator during most of the 1960s, recognized that the Apollo missions had to also be science missions. This was a scientific opportunity unlike any other. The chance to get up close and personal, literally, hands-on, with the moon itself. But at the time, the idea that the Apollo mission should have a scientific component was not popular at all. NASA was a political tool. It was an administration tasked with a very specific set of purposes: to propel the United States into space and, after Kennedy's famous speech, to beat the Russians to the moon. And while science is a part of making that possible, it's not the end goal. So Webb and other leaders faced stiff resistance. The public and political leaders were not interested in spending vast sums of money on a little science expedition. Things haven't improved much in the decades since, and even many scientists were opposed to it. They were worried that the absolute buckets of money being poured into Apollo would mean that moon science would take resources away from any other kind of science, especially planetary science, which was a field still in its infancy. But nowadays, NASA is seen as a science-first organization, and it was the Apollo missions that enabled that switch. And the science prioritized in the Apollo missions wasn't planetary science or astronomy or even physics. It was geology. If you haven't noticed yet, the moon is made of a bunch of rocks. I know, I wish it was made of cheese too, but it's rocks. Rock outcrops, rock plains, rock mountains. Big rocks, little rocks, fat rocks, skinny rocks, all the time. The Apollo astronauts were going to spend quite a bit of time on the lunar surface, and the thinking was, well, if science can't be a priority, we should at least give them something useful to do while they're waiting for their ride back up. Right away, geologists like Dr. Burt King answered NASA's call to become personal astronaut trainers. Not training in being an astronaut, but training astronauts to be geologists. Very quickly, the geologists found that the astronauts did not much enjoy their classroom lectures. These were fighter pilots and risk takers. They started getting agitated, fidgety, and made their complaints quite plain. So the geologists switched gears and took them on field trips, squeezing in training sessions whenever time would allow. The first training session took place in the Grand Canyon. Dr. King figured that the awe-inspiring majesty of the canyon would serve as a lure to draw the astronauts into the science of geology. They were moderately successful, with some astronauts becoming absolutely engrossed, and others, well, less so. But the geologists had one thing in their favor. Regardless of their personal interest in geology, the astronauts were a highly competitive bunch, and a belief quickly spread that the better you were at fieldwork, the more likely you would be selected for a landing mission. This belief was misguided. Mission planners couldn't care less, but the geologist teachers did nothing to dissuade their students from this notion. After the Grand Canyon, training exercises took place in Big Bend, the Philmont Ranch in New Mexico, and other places in the American Southwest. The geologists knew that these places were nothing like the moon. Most importantly, much of the geology of the Southwest is driven by plate tectonics, weathering, and water-driven processes, all of which the moon lacked. But the variety and scale of geological formations allowed the teachers to give a master's-level crash course in field geology to the astronauts in the limited time they had with them. Those places were also close to local infrastructure, as the nightly beer runs would attest. In those training sessions, the geologists taught the astronauts the ins and outs of fieldwork. What to look for, what certain structures or patterns signified, how to identify areas or objects of interest, how and when to collect samples, how to take proper measurements and what tools to use, how to describe verbally what they were seeing, how to compose a photograph that served scientific, not touristic purposes. Each of the Apollo missions carried a package of scientific instruments called, appropriately enough, the Apollo Lunar Surface Experiments Package. Except for Apollo 11, because the full package wasn't ready yet, science wasn't the priority, remember, so they had the early Apollo Scientific Experiments Package. And this package was everything you could ever need in a field expedition. A passive seismometer, a magnetometer, a solar wind detector, an ion detector, a heat flow detector, and an active seismic experiment. Plus all the usual low-tech geology gear. Hammers, picks, pokey sticks, tongs, scoops, tubes, drills, reacher grabber things, gnomons, rakes, trenchers, wire brushes, lenses, scales, bags, containers, buckets, and don't forget the toolboxes to carry it all. Plus, their most important tools of all, their own eyes and hands. The astronauts, with all that geology training, could see things that mission control couldn't. They could walk over and grab stuff. They could investigate it and decide if it was worth keeping. They could do active field research on our first encounter with an alien world. By the time of Apollo 17, a literal geologist, Harrison Schmitt, went to the moon. And although there was technically a mission plan, he was basically calling the shots himself. And what they learned would transform everything we know about the moon. A set of instruments shut off almost 50 years ago are still producing useful results today. It's the seismometers left by the Apollo missions to monitor moonquakes, which, as the name suggests, are earthquakes, but on the moon. First off, the Apollo seismometers were the first to reveal that the moon does indeed have quakes, which is an impressive achievement in its own right. And once we realize that the moon shakes, we've been able to use the natural seismic vibrations produced inside the moon to map out its interior structure. It's the same way that we can map out the interior of the Earth. Vibrations travel at different speeds through different kinds of materials, just like sounds are different in the air versus underwater. The reason that the Apollo-era seismometers, which were shut off in 1978, still provide useful results is that even though they're not producing data, our analysis techniques and understanding have improved. This means we can squeeze more information out of the data we already have, and decades after the seismometers went silent, we were able to use their data to find evidence for the existence of the moon's core. So the moon's got a core. That's nice, but what's the big deal? The big deal is that it's best to stop thinking of the moon as merely the natural satellite of the Earth. Instead, think of it as a small, rocky terrestrial world in its own right. It's stepping out of the shadow and into the limelight, and it's got something to say. I'm reframing this because the moon is our keystone to understanding how all terrestrial planets, Mercury, Venus, Mars, and yes, even Earth, evolved in their early history. That's because the moon still retains a record, a memory of its younger days, frozen in place for billions of years. The Earth doesn't remember most of its ancient history because all of our plate tectonics. We haven't landed on Mercury. We've technically landed on Venus, but that wasn't for very long, so it doesn't count. And yes, we've landed on Mars and even collected some samples, but we haven't figured out how to get those samples back to Earth. So not only does the moon retain a memory of what all terrestrial planets go through, it's right there. And we've been able to touch it and bring some back and smell it. By cracking open moon rocks, by looking at seismometer data, by looking at core samples, by looking at heat flow data, we can piece together what happened on the moon and use that knowledge to inform what happens on Mars, Venus, Mercury, and Earth. And what happened to the moon was, put simply, not very pretty. We now know that there was a phase, shortly after it formed, when the moon was covered in a single magma ocean with a depth of around 500 kilometers. What we call the lunar highlands are simply the slightly less dense rock that floated to the surface of that magma ocean and then solidified first. What floated to the top and cooled was largely minerals containing oxygen and silicon, with iron sinking down to form the core. Hey, wait a minute, that's exactly like the Earth. I told you. The moon could tell us about our own planet. Shortly after the surface of the moon largely cooled and the crust formed, it suffered a series of intense impacts, an epoch between 3.85 and 4 billion years ago called the Late Heavy Bombardment. Just strike after strike after strike, like a brutal, uneven boxing match that you just can't look away from. Each of those impacts formed breccias, which comes from the Italian word for rubble. Why we didn't just call it rubble, I don't know. Breccias are formed when you have a bunch of different kinds of rocks and minerals doing their own thing, minding their own business, and then wham, a meteorite comes crashing in, smashing and mixing and fusing everything together, and then all those minerals are forced to cohabitate in the same rocks. Finally, after the late heavy bombardment, the moon suffered periods of major volcanism, which would explode and pour liquid hot magma across their surroundings, generating the mare, or seas, that we see today. How do you tell how old an astronomical object is? I mean, next time the moon is in the sky, take a look at it. How would you even begin to answer that question? Well, a good first step is contributing to Patreon. That's patreon.com/PMSutter, where you can contribute to this show and keep it going. I truly appreciate all of your contributions. That's patreon.com/PMSutter. Astronomers use a technique called crater counting, and it's pretty much exactly what it sounds like. The idea is that a world like the moon, Mercury, and many of the moons of the outer system are not active. They've been dead in almost every sense of the word for a very long time. When a comet or asteroid strikes them, the crater they leave behind sticks around. There's no air to blow it away, no water to wash it down, no plate tectonics to pull it under the surface. And so craters just pile up one after another and often on top of each other. But not all dead worlds are created equal. Some of them were molten in the recent past, and lava is really good at covering up craters. So if you compare two worlds and count their craters, you can get a relative sense of which world solidified sooner. And some had molten parts alongside the solid parts for some amount of time. Planets and moons don't always cool all at once. There might be active volcanic regions over here and just plains of solid nothingness over there. So if you can scan across the surface of a world, the places with more craters are probably going to be older in the sense that they solidified in the more distant past than the places where there are fewer craters. For example, on the moon we have those two broad regions, the dark basins, or mare, and the lighter colored highlands. Just by looking at the craters, you can tell that the maria are younger because they have fewer craters. But how old? If I see a world with tons of craters, how old is it? Not in a relative sense, as in this planet is older than this other one, but in an absolute sense, like billions of years. Give me a number. The Apollo missions held the key to unlocking crater records not just on the moon, but across the solar system. That's because scientists have been able to apply radiometric dating to the moon rocks returned from the Apollo missions. If you're not already familiar, radiometric dating is where you look at the abundances of various radioactive elements and compare their proportions to the numbers of elements that they decay into. Since we know the half-life of those elements, we can calculate the absolute age of that sample. And since the Apollo missions visited many places on the moon, we've been able to build a detailed accounting of which parts cooled and solidified when. For example, the edge of the Sea of Tranquility, the site of the Apollo 11 landing, is just over 3.5 billion years old, while some other regions in the highlands reach right up to the 4 billion year old mark. By far, the youngest features on the moon are some of the large impact craters, like Copernicus and Tycho. These craters are all less than 1 billion years old. The youngest crater of all is probably the Giordano Bruno crater, named after the Italian Renaissance smart/crazy guy, different story, and it's only 4 million years old. These craters are so young because the impacts carry so much energy that they're able to erase everything in their vicinity, wiping the slate clean and starting the whole process over. With these absolute numbers in hand, we can now calibrate crater counts across the solar system. Now we can look at regions of Mercury or Callisto and know how old they are, even though we've never been there, thanks to the Apollo missions and their geologic handiwork. We also know, thanks to the Apollo missions, that the moon is slowly slipping away from us. This was hypothesized all the way back in the early 1800s when Sir Edmund Halley of Halley's Comet fame read through ancient eclipse records and realized we were slowly getting further and further apart. And we had a pretty good explanation for why the moon might be going away. The tides raised by the moon get carried in front of it by the spin of the Earth, and then extra gravitational tug pulls the moon into a higher orbit, but we had no good way of putting a precise number on this. In 1962, Princeton graduate student James Fowler proposed placing reflectors on the moon's surface. This would allow us to more easily bounce lasers back and forth from the moon to here and use that to measure a distance. The same way you can use one of those little laser measurement thingies to, measure distances. While measurements had been taken before by just reflecting off the lunar soil, with the reflectors placed by the Apollo missions, the measurements became much more accurate. We now know that the moon is receding from the Earth at an average rate of 3.8 centimeters per year, which isn't very quick, but over the course of, an eon or two, it really adds up. In fact, in just a few 100 million years, the combined effect of the moon spiraling away from us and the sun getting brighter and larger, a different episode, will mean that total solar eclipses will become totally impossible. So, enjoy them while they last. If you think about it, and trust me, we're about to, the moon is kind of weird. Of all the terrestrial worlds of the solar system, we're the only one with a substantial natural satellite. Mercury and Venus have nothing. And while Mars technically has 2 moons, they're really just captured asteroids and don't really count. I'm sorry, Phobos and Deimos, but that's the way it is. Our moon is huge, at least relatively speaking. It's 1.5% the mass of the Earth, which is bigger than any other ratio with the exception of the Pluto-Charon system. So we gotta ask, how did we get our big old moon? In the early 20th century, there were dozens of ideas floating around academic circles. Maybe the moon was a still-forming protoplanet that we captured. Maybe when the Earth was still molten, we were spinning so quickly that we flung off a chunk like when you stir cookie batter too hard, and then that became the moon. Maybe the moon formed on its own from the collision of several smaller objects in Earth's orbit. Or maybe none of the above. And what did the trick was the Apollo missions. While there are a lot of observations we can make about the moon from the comfort of our own homes or observatories, or from orbiting satellites, that's not enough to resolve the question of where the moon came from. The Apollo missions hit pay dirt, or pay regolith, whatever. With the samples those astronauts collected, we found one key piece of information. One was the unmistakable evidence that the moon was once highly molten in its past. The whole globe-spanning magma ocean thing. Many of the rocks on the lunar surface are igneous. They're solidified magma. And plus that, they're creepy. Hold on, I'm serious. This is a real thing. Many lunar samples are called creep-rich, where creep is, of course, an acronym. The K is the symbol for potassium. REE stands for rare earth elements, and P is for phosphorus. See? Creep. It totally makes sense, and I swear that was not made up on the spot as a joke. The point is that these elements don't usually hang out together. And the only way to get them in high concentrations in the same rock is to liquefy the whole dang thing. This gives those elements quite a long time to get together. So yet another piece of evidence that the moon was molten, which requires a lot, and I mean a lot, of energy. The second major piece of evidence is the oxygen. Yes, the moon has oxygen, a lot of it in fact, but it's bound up in rocks, just like it is on the Earth. And there are some isotopes of oxygen that are stable, meaning that they don't experience radioactive decay. The moon has the same proportion of these stable isotopes as the Earth does, which is way more than a coincidence. But there are also some key differences between the moon and the Earth. The moon has a lot fewer heavier elements, and like absolutely zero super light elements, just has the middle stuff. How do all these pieces fit together? They fit together with the giant impact hypothesis. This is the idea that when the Earth was still forming, we were struck by a Mars-sized protoplanet named Theia. Theia, by the way, was named after one of the Titans of Greek mythology, the daughter of the sky and the earth, who eventually got imprisoned forever for the crime of, just being a Titan. Anyway, the collision released not a little bit of energy and sent a chunk of the Earth and some bits of Theia into orbit around us. Those bits became the moon. This explains the common isotope ratios. We're made out of the same fundamental stuff. And it explains why the moon had deep magma oceans, which are our favorite kind of magma oceans, because the whole scene just kind of blew up. And it explains why the moon doesn't have a lot of heavier elements like iron, because all of that sunk to the center of the Earth. And we have an extra large core thanks to that. And it explains why the moon lacks any really light elements, because all that got vaporized in the collision and it didn't have enough gravity to hold on to it. The giant impact hypothesis is now the most common belief among scientists as to the origins of the moon. Without the Apollo missions, we would have a much less complete picture and be much less sure of our conclusions. Any one of these advances in science, the composition and structure of the moon, the calibration of cratering rates, and the linchpin evidence for the giant impact hypothesis could have justified the Apollo missions. But we got all three, plus more that I haven't even talked about yet. And that's just the science. There's also the enormous technological progress, the spin-off technologies, the advances in engineering, materials, orbital dynamics, the list goes on. Scientifically speaking, the Apollo missions were an unqualified success. Plus, we got to land on the moon, which is incidentally pretty cool in its own right. The next time we start debating the value of future crewed missions to the moon or Mars, I want you to keep all this in mind. We know a lot more about how the universe works thanks to the Apollo missions, all for a measly 12 and a half days on the surface. Imagine what we could learn if we stayed there. So what do you think? Did the scientific results alone justify the costs of the Apollo missions? And as we look ahead to Artemis and other initiatives to return to the moon, what science goals should we prioritize? Let me know what you think in the comments. Thank you for watching, and we'll see what the future will bring.